Now let's work another nodal analysis problem. And in this case, I'm going to take this circuit and I'm going to apply the first two shortcuts we've already used. And in addition, there's something else that's interesting about this problem. It's the fact that it has a dependent source in it where there's a current Ix flowing through this 10 ohm resistor, and I have a current-controlled current source, which is equal to 2 times Ix. Let's work this problem, and let's see how few equations are really required in order to make it work. All right? So let's go through and let's solve for all the node voltages. And if we look at this, there are really only two essential nodes. The node along the top, the node along the bottom, and the only other node is the node between those two resistors, but that's a non-essential node. Those two resistors are in series. So in this case, I can pick one of these nodes to be ground, and it looks like I've got an equal number of branches for either one, so I'm just going to pick the one on the bottom to be equal to ground. And then I'm going to go and call this top node, give that a variable value of V1, voltage V1. Okay? Now let's go through and let's specify our currents. We've already specified our nodes. Now, this current's already given by the problem, Ix. There's no point in changing that or using that or making that any different. Let's just stick with what we got. For these resistors, I'll pick a current flowing downward and a current flowing downward through both of those resistors together. And once again, me picking a downward current is strictly my choice. It's arbitrary. I could just as easily pick them to going up and I would still get the same solution. So, having drawn the directions, let's add our voltage drops across our resistors according to the passive sign convention to make sure we don't make any sign errors when we write our equations. And now let's go ahead and solve. Well, in this case, KCL plus Ohm's law. There's really only one equation we need to write. And in this case, 10 going in and 2Ix going in must be equal to V1 minus 0 over 10 plus V1 minus 0 over 40 plus V1 minus 40, pardon me, V1 minus 0 over 40. Or just 25 plus 15, 40. Okay? So, here are my equations. I've written my KCL equation. There are no other KCL equations I can write for an essential node. There's only one problem. I can't solve this. And the reason why I can't solve for this is because I've got two variables but only one equation. I need another equation. And what I need is the dependent source variable equation. I've got a dependent source in this circuit. It uses Ix. I need an equation for Ix. And I need that in terms of node voltages. How do I write Ix in terms of node voltages? Just like this. My dependent source variable equation is that Ix must be equal to V1 minus 0 over 10. That's my second equation. Now I have two equations, two unknowns. Now I can solve. And if I solve, what I will get is that V1 is equal to minus 200 volts and Ix is equal to minus 20 amps. Okay, if there is a dependent source in your circuit, for every dependent source, if you have two dependent sources, you need two dependent source variable equations. If you have three, you need three equations. But for every dependent source, you need to define the variable that's used in that source in terms of node voltages. Otherwise, you will not be able to get an answer. So I needed both of these equations in order to solve. All right? Now there's an exception to this. What if my dependent source variable is a node voltage? So what, for example, if this was equal to 2V1? Well, in that case, the dependent source variable is just a node voltage. And there's no additional equation I can really write. So the exception is if the dependent source variable is just a node voltage. So as you keep working nodal problems, you're going to see several problems that are going to include dependent variables. And you need to always remember, watch out for that dependent source variable, the DSV. Make sure you include that equation or else you're not going to be able to get an answer.